How's it going, everyone? It's John again. Today's video I'm going to do a demonstration on how to configure a rooted access design within a campus environment. Now, I actually got this request a couple of days ago in my comment section from a user called Mr. B, so this one's for you. And it kind of fits in with what I've been planning anyway. For the past little while, I've been thinking about having this kind of packet tracer lab series, in which case I write up some kind of lab and perform it from start to finish, but break it up into little chunks. So maybe every 10 minutes I'll stop the video, save the packet tracer file, upload it for the viewers to actually download, and then they can continue along each step with me. So perhaps if you didn't get one section working, you can just skip that and go on to the next section. Or if you just want to start from part 3 of 6 rather than having to start from the very beginnings, if you know how to configure VLANs, for example. So that's been my plan to do that, and this is what I'm going to do in this video. I'm going to go through the process. I don't know how long it will take. It might take me 15 minutes or 45 minutes or longer. I've really no idea, depending on how much I chat. But what I will do is I'll try to regularly save so it's in digestible chunks, and each section will be uploaded. So without further ado, let's discuss what we're going to do here. Okay, a rooted access design. What actually is that? Now, contrast to the classic 3-tier hierarchical model, you would have your core, your distribution and access layer. That still exists. There's nothing different here. However, classically what you would do is you would build layer 3 connections between the core and the distribution layer. However, between the distribution layer and the access, that would be running layer 2. And typically what you would do would be to construct a first hop redundancy protocol like GLBP, HSRP, VRRP in the distribution layer to provide some kind of gateway redundancy for the host down here. You would do other techniques like you would map your spanning tree, your root bridge to your HSRP active router, so to avoid extraneous hops and just get the most direct access for optimal traffic paths. By using a rooted access design, you're kind of skipping all that. What you're doing is you're running layer 3 from the core to the distribution layer and the distribution layer right to the access layer. Now, this actually provides many benefits, and it does have some drawbacks. I must actually say that there's not. This is not just a catch-all, perfect solution for every network deployment. In fact, over on the right-hand side here with the server farm, I've actually included the kind of original classic multi-layer design in this one, just purely because very often in a server environment you actually require wide spanning L2 adjacencies, and you can't just truncate each or terminate rather each subnet at each access layer switch. You need that whole broadcast area. This is to do with applications requiring L2 adjacencies. Some applications like Apple's Bonjour protocol is notorious for that. It does require layer 2. And because of virtualization and just copying virtual machines between servers rather, they have to be on the same network. So these things do present problems. There actually is ways around them using stuff like VXLAN and stuff like that, but this is way out of the scope of this video using Packet Tracer. You can't configure anything like that on Packet Tracer. So what I've got here is the old classic way for the server farm and the rooted access up here. Now, I've made a few notes here which I want to just skim over just so you can kind of see. These are the kind of advantages and also just little points you need to make, and I've listed some disadvantages, so let's just quickly look through them a wee second. Okay, so rooted access advantages. Okay, there's no spanning tree feature placement, so you don't need to worry about where your root bridge goes or loop guard. That's taken care of. Spanning tree is only affected at the very southbound edge of the network. See here? This part here which connects to the hosts. All here, there is no spanning tree at all. So that is simplified massively there. There's no requirement for a first hop redundancy protocol, your HSRP, VRRP, GLBP, and you don't need to tune timers or align that with the spanning tree root bridge, obviously. It simplifies multicasting, so rather than having your PIM designator router and the IGMP querier, they don't have, ordinarily in this case you would have the PIMDR and your IGMP querier here. When you move this to the access layer, this one access switch acts as both for this network. Same, this one for this network, this one for this network. So it's not shared between two separate control planes. It's simplified, and because of that, it's you don't get any kind of weird L2, L3 topological inconsistencies. So that's another note. No trunking required, don't need to do that. No management VLAN, you actually just use loopbacks with /32s. You get intelligent load balancing. Here's a big one, right? When layer 2 fails, it fails open. Now, what does that mean? You get broadcast storms, which are difficult to isolate and troubleshoot because you don't know where they are. They actually just kind of propagate around the network and can actually bring down potentially the entire network. You have what is commonly referred to as an increased blast radius. So one little problem on one device can cause a storm which affects multiple devices and you can't locate it. The difference is with layer 2, when layer 2 fails, it fails closed. It doesn't broadcast a big storm throughout the network. You just get an isolated neighbour loss. Some subnets fall down, but it's contained to a small region and it's easy to identify because you just see this subnet go down and you know, okay, it must be in this little isolated segment in the network which has failed, and you can go troubleshoot that area much easier, especially when you're pressured by upper management to keep the network up. If you can't find that problem and just money's going down and you can't find it and the network's still down, you would wish you would have a simple solution, and layer 3 everywhere kind of provides that. You get increased link utilization, obviously. All your links are forwarding because you don't have spanning tree blocking links. Here's a big one. You want to be building triangles and not squares so that each path is equal in cost. What I mean here is, see these parts here? You want to have triangles because that means that for every single path, it's equal cost. And because of that, you get to use, Ceph will just use ECMP, equal cost multipath. So what that does effectively is when you have an upstream failure, like from this point of view, if you have equal costs to get to every network, like this switch here will have every exit will use that, and the links are the same cost because they're same bandwidth and they're the same hop distance, so they're the same cost. So it will load balance across them. So what happens if, say for example, this switch happened to fail, rather than getting an OSPF or an EIGRP recalculation, it just calculates the reroute locally within the switch or the router the way it's acting now, and it just reroutes and sends out the alternate path. The only way you get an actual routing protocol recalculation is if one of the access one fails, because they're actually connected to separate actual networks, so it's actually desirable that it does update the routing protocol so it says here this network is completely black hole, we can't get to it, and that will cause a reconvergence. But the upstream, if that fails, it just reroutes it the other way. Same here, if this one fails, go that way, this one fails, go that way, so on and so forth. So you get this super fast failover. Same thing here, if a core one fails, drop off and go the other way, because it's load balancing anyway, and it just is calculated locally within the router, so it keeps it really tight and really crisp. What else have we got here? What else did I write? Yeah, upstream recovery, downstream, I talked about that there. Okay, you want to use layer 3 routed links and don't peer over your VLAN SVI. So what I mean here, on the access layer, we're still going to use interface VLANs for the access. So VLAN 10 here, we're going to have interface VLAN 10, interface VLAN 20, interface VLAN 10, interface VLAN 20, so on and so forth. But you're not peering with the router up here with that. You're actually converting all of these links to no switch ports and connecting directly over the physical link. That's the way you're peering your OSPFs over the physical link. The reason why is because when you do it via SVI, you get two additional states. You get auto state and SVI down, and that adds a lot of milliseconds to the failure detection. It might not seem like a lot, but you're talking like maybe 150 milliseconds more, which is a lot when you're dealing with stuff like voice and video and so on and so forth. So just using physical links speeds it up. It keeps things very efficient. Do it that way. What else do we have? Oh yeah, you want to summarize to the core to limit event propagation and reduce shortest path forward calculation. So that's what you want to do. You want to have all these distribution layer switches. You want to make sure all these addresses are summarizable, which is why I've made that like 10.10, 10.0, 10.10, 30.0, 10.10, 50.0, and 60.0. So all this block can be summarized as 10.10.00/16, and you summarize that from the point of the distribution switch. The same thing happens with all the other distribution switches. So, what else do we have? Yeah, this is one you can't do in Packet Tracer. There's a phenomenon, if you want to call it, called Ceph polarization, in which case the Ceph hash values, it will look at the source destination IP or MAC address or whatever, and because of the input values, the input parameters, it calculates it one way, and that tends to repeat itself throughout the network. So what I mean there is that if the packet comes here and Ceph calculates to take the right path rather than the left path, it will come to here and make that same decision here. It'll take the right path rather than the left path, and same again here, it'll take the right path rather than the left path. So what you want to do is build in some randomness to that so that you get full link utilization. So you're not just getting this predictable right, or left. You're getting this right, left, right. So you're really using all your links. And the way you would do that would be to change the Ceph hash value in the distribution layer. Leave it at default in the access in the core, but distribution layer mix up so you get that kind of randomness. That can't be configured in Packet Tracer, however, so don't worry about that. That's just a note to if you're doing it on Real Gear or perhaps GNS3. Yep, so what you want to do is your loopbacks, you want to fit that into the block summary range so they can be summarized as well. They're going to act like your management interfaces rather than the management VLAN. You're going to connect to the switch via a /32 loopback. Don't put the loopback in area 0 though, because if you put it in area 0, let's say this connection drops out, because you still have a connection to area 0, so the switch thinks it will still propagate the default routes down here via the totally stubby configuration, which I'm going to explain in a second. So because of that, what happens is it basically gives us false reading that it's still connected to area 0, and you'll equal cost load balance to it even though it's not directly connected. What you want to do is fail over here. So take the loopback and configure it in a separate area. In this case, we've got area 10, area 20, 55, 66. So what I'm going to do is all of the core facing interfaces as well as all the core interfaces will be area 0. See the links between each distribution switch as well as the loopbacks and all the LAN facing interfaces, that's going to be in area 10. Same again here, the links between the distribution and the loopbacks and the LAN facing interfaces, area 20. Same here. So that's the way it's going to go. So they will be configured for area 20. And what you want to do as well is to tighten everything up. What you want to do is make all of your distribution switches, you want to configure them so that they're propagating just default routes for the rest of the network. By doing so, you basically convert this area to a totally stubby area. So you're going to go in here and do area 10, stub no summary, area 10, stub no summary, and just on the access layer, area 10, stub all these. Up here, area 20, stub no summary, area 20, stub no summary, and here, area 20 stubs, all on these. This is going to keep things very tightly constricted, such that you're just going to have these default routes equal cost load balanced out in conjunction with your summarization. You're going to have this really tight, stable network. So let's just quickly discuss some of the disadvantages. It can be harder to initially plan and implement, although it's far more stable when it's up. So you've got your L2 adjacencies. So some, like I said before, some require L2 adjacencies which need to be wide span, and this happens very often in server configurations. So if your VLANs must span, you can't have rooted access. The rooted access works with a single access switch to a single VLAN to a single subnet. That's what you want. You can have multiple VLANs on the same switch, but they can't span. If you actually notice, you think this might be VLAN 10 spanning across here, or maybe spanning across all 6. They're actually not. These are all 3 separate, or rather 6 separate VLAN 10s in this case. 6 separate VLAN 20s. They're not the same. They're different subnets and they're routable to each other. So even though in name they're still VLAN 10, they're not VLAN 10 the way all of this might be VLAN 100 or VLAN 200. They're actually all separated. So if you can separate them, you can do this. If you need that wide broadcast area, that east-west broadcast, then rooted access is going to present some problems. You might need to look at VXLAN and stuff like that, which could be a bit more complicated and involved. Another thing you need to pay attention to is L3 switches. That's what you need because it's routing. They are more expensive. They're a lot less expensive now, so it's still more feasible to do so. You can get, let's say, a basic license which does stub routing and kit out all your access layer just with, is it 3650s I think does that, with your basic routing license. You don't need the full routing license, and you can get it pretty cheap. So you can still, it is cheap compared to what it used to be, but it is still a bit more expensive than a basic, say, 2960. What else have we got? Yep, here's the last thing I want to talk about is segmentation strategies like VRFs. Because they're moved southbound to the access layer, you need to it does require more configuration. So rather than just aggregating it all at the access layer, you're going to have to do more configuration. That is just purely a function of, now it's not really visible in this configuration because it's just a small topology relatively, but generally in the wiring closet you would have a lot more access switches. You would have maybe, let's say you had 20 access switches here and 20 here and just a few distribution layers. If you just had to configure in the old classic way, VRFs, your layer 3 VRFs here, you would just need to configure it 1, 2, 3, 4 here. If you've got lots and lots and lots of access switches, you need to do your VRFs on all those switches. So that is a trade-off. If you've got a lot of access switches and you're going to do a lot of layer 3 segmentation, you're multiplying how much you need to do just to get that. So that's pretty much the basic overview of the configuration. There's no configuration done in this video yet. I'm just going to stop it now, and then from the start of the next video we're going to kick off and go straight from the configuration. I'm going to save that packet tracer, upload it, and then the next video will start from where I left off. Okie doke. So thanks for watching. Come back in part 2 and we'll start doing configurations. See you guys soon.